Now, just imagine this, traveling almost anywhere in the world in just a matter of hours. What you're looking at here is Boeing's initial concept of a passenger-carrying hypersonic airplane. Across the company, our engineers are studying the technologies that could one day make this a reality. Hey everybody, I'm Adam Mertz with Boeing Communications, and joining me is our hypersonic expert, Kevin Bocut. And Kevin, this really is a glimpse into the future. What an incredible concept.
Pretty neat. Pretty excited about this.
What makes it so special? Talk to me a bit about it for folks out there who may have a little bit of knowledge about the hypersonic, but what can this really do?
Well, the thing that makes it most special is how fast it flies. Mach 5, 5 times the speed of sound. For anyone that's traveled across the ocean, takes 6, 12, 14 hours. This will get us there in 2 to 3 hours, shortening the trip to the point where you could literally go to Europe or Asia back and forth in a day.
And we were talking about this earlier, but how fast it travels per second. Yeah. That is a really important thing to point out to people because it's really mind-blowing.
It's really fast. So Mach 5 is a mile per second, which is 3,600 miles per hour.
So you blink and it is already gone.
It's gone. It's faster than a speeding bullet, as they say.
And what you're holding there is the concept model. Walk us through the design concept, why it looks the way it does, and point out particular features that really make this unique.
Well, there's 3 key features. One is you'll notice it's very sleek. It has to be for low drag. Flying it this fast, we need high lift to drag ratio to get good cruise performance, so that means low drag. It's also shaped to ride on its own shock wave. So the wing creates a shock wave that it rides on like a surfboard. We call that a wave rider. The other 2 key features is what it's made out of. The faster you fly, the hotter the skin gets, the structure gets because of friction, air friction. So this, flying at Mach 5, it's about 1,100 degrees Fahrenheit, maybe a little hotter. On the leading edges, it'll be even hotter than that. But it turns out we can make that kind of a structure at those temperatures with an advanced titanium, so nothing real exotic. So it's important what you make it out of to deal with the temperatures. And the other one is the engine system. Going that fast, you can't use just a traditional turbofan or turbojet engine. So it's what we call a combined cycle engine. It combines 2 different cycles. One is the turbine, and we envision this to have a derivative of a commercial airplane engine, a modified turbofan, but we add an extra element. In this case, it's a ramjet engine. So when you take off and you're flying at relatively low speeds, you have to have compressors and blades inside of the engine to compress the air and get propulsion. But when you're going fast enough, just the motion through the air compresses the air through shock waves. You don't need those anymore, which is good because the air gets too hot and you would melt all that turbo machinery. So at some speed, maybe Mach 2 or 3, we actually transition and we bypass the air into the ramjet, which is basically an afterburner behind the turbojet. And those are the key features.
So you're talking about flying high, flying fast. The big question we get from a lot of people is, what will it be like to ride on one of these aircraft?
Yeah, what does it feel like? Well, it'll be amazing, but it won't be scary because we don't feel speed. A lot of people, can you withstand Mach 5? Yeah, when you fly in a commercial airplane, you're going over 500 miles per hour. You don't feel that. If you're flying in space around the Earth, you're going 17,500 miles per hour. You don't feel that. You feel acceleration. So what you'll feel here is the acceleration of takeoff and getting to Mach 5 speed, but it won't be it'll be familiar to you. When you take off in a subsonic commercial airplane, you accelerate at about 1/3 of the force of gravity for half a minute to a minute. You kind of get pushed back in your seat. The difference here, this will be 10 minutes. You'll feel that gentle pushback for 10 minutes as you accelerate to Mach 5 and about 95,000 feet. That'll be the other cool thing about the experience is flying that high, you'll see the curvature of the Earth below you. You'll see the black of space above you. It'll be a pretty neat view.
Now, if you're just joining us here on Twitter as well as Facebook, I'm here with our hypersonic expert, Kevin Bocut, talking about our new initial design concept for the passenger-carrying hypersonic. This is something that will be on display at the Farnborough International Air Show next week. We have a larger model that will be there. And one thing we want to point out, this is really just a concept. We're working on several different designs, and this is still, we're talking decades out. Give us an idea of what technologies we're working on to make this happen and when people can expect to possibly see something like this.
Yeah, we anticipate it'll take 20 or more years to mature everything. A lot has to happen. The design has to mature. The technology is pretty mature, but the market, regulatory. Right now, you can't fly supersonic across the United States. So a lot of things have to come together to make something like this happen. But we believe it's doable. And we are studying different designs. This is like our first concept. But we're looking at different ways to shape it, how to integrate the engines. You'll see under here, it's got two different engines, or two engines. And in them, the engines are in line with each other. So there's two of them. You got the turbo machinery, and behind that you have the ramjet. How we integrate those onto the airframe, whether they're on the center line or outboard on the wing, we're looking at all those types of variations right now.
And when we're talking about this, my mind's just swirling with questions, and I know a lot of people out there have questions as well. So go ahead and put your questions in the Facebook comment section. Also, tag us on Twitter. We'll start trying to answer some of those, and we're already getting a couple that have come in. One from Luca, who wants to know, how many passengers will this aircraft hold? Can you talk a little bit about that, or give us any sort of idea? Or
Sure.
is that still too far out to really?
It's too early to say. What we're doing now is we're actually studying a range. The market will determine what the right number of passengers is. So right now we're looking at smaller numbers and larger numbers and getting a feel for how the plane changes, how the design changes, how big it is, and the economics.
With this type of aircraft, it's certainly changing the way, or it could change the way that we fly. Give me the specifics in terms of how high it flies. What makes it different than everyday air travel today?
The primary difference is how high and how fast it flies. When you fly fast, you have to fly higher due to air pressure. The faster you go, the higher the pressure. So you go to higher altitudes where the pressure is lower. 95,000 feet, and of course Mach 5, where you can zip across the ocean in 2 to 3 hours, get to London and back in a day, or Asia and back in a day. Pretty cool.
One of the things that I saw is that you could actually get from Sydney to LA in 4 hours.
Yes.
Truly incredible. I mean, when you think about
That's
that,
a
that
long
really is.
flight. I've done it. I've done it. You know, you arrive at LA at 10 at night and you fly, 14, 16 hours, sleep the whole time, eat a couple times. It's a long flight.
And in looking at this concept that we have here, what makes this different from the Concorde?
Well, first of all, it's 2.5 times faster. So Concorde was still made out of aluminum. This will be made out of titanium. Titanium's in a lot of airplanes today, commercial airplanes, but the entire airframe is not made out of titanium. The SR-71 was made out of titanium, for example. So it is twice as fast, and it's got to be shaped differently, and it's propelled differently. The Concorde had a turbojet engine in it, so it didn't have to go to that ramjet mode, whereas this, we have to go to that higher speed propulsion technology.
And this isn't something you just do overnight. Boeing's been working on this type of technology for decades. Talk to me a bit about that, because you've certainly had a hand in that.
Yeah, we've been involved in hypersonics for 6 decades. It goes back to the late 50s, 1960s, where we designed, built, and flew the X-15. That was an experimental hypersonic airplane. It was rocket propelled, it had a pilot in it, and it was carried by a B-52 up to altitude and dropped. And in the 60s, it actually flew up to Mach 6.7. So it went hypersonic with a pilot in it. It even went out of the atmosphere into space, not into orbit, but suborbitally into space and back down. So we worked on that. That technology development led to the space shuttle, for example, and it led to the X-37, which is flying today. But spring forward 50 years, that was rocket propulsion. Rocket propulsion is not an efficient way of going from point A to point B on the Earth. You have to carry the oxidizer, you use a lot of propellant, a lot of challenges like that. So to go fast, you need air-breathing propulsion, where you're actually using the air in the atmosphere to oxidize the fuel. So spring forward 50 years, we also worked on scramjet technology and flying scramjets.
And that's what we're seeing here on our screen.
That's what we're seeing here. So back in 2010 through 2013, we flew 4 times the X-51. Notice the transpose X-15, X-51. That was done intentionally. This was like the next generation of hypersonic technology, using air-breathing propulsion called a scramjet, supersonic combustion scramjet. So you see, it's also carried by the B-52. It was dropped, rocket boosted up to Mach 5.8. The booster then separates. The dual mode scramjet comes on. Dual mode means it starts as a ramjet, as it accelerates, it transitions to scramjet, and it actually flew to Mach 5.1, which is just barely faster than the plane we're talking about here. So we've flown at Mach 5 with an air-breathing engine, and that's the kind of technology we're applying here.
And how long does it take to develop that? I mean, a lot of times people will see something like this, and these are tough problems that we're trying to find solutions for, and we're advancing that type of technology.
Well, from the idea of a scramjet, a supersonic combustion, from when it was first conceived to when we actually demonstrated in flight was about 50 years. So it was a hard problem. It took a while to figure that out. But now that we've got it and we've learned those lessons, we have the technology, now we're thinking of ways of employing it for practical applications like this one.
Now, if you're just joining us, what you're looking at here behind us and then the model in Kevin's hands is our concept, our initial concept for a hypersonic passenger carrying aircraft. We're taking questions from you also. Continue to have those come in. One from Joseph Peck. He wants to know, are we
Yeah, we
working
Boeing.
with NASA to reduce the sonic boom or sonic boom reduction technology?
That's a great question. The answer is yes, we are. This is a big program in NASA. They actually want to do a flight demonstration to show low boom. We've worked with NASA every step of the way, and we want to employ that technology. We're also studying supersonic airplanes that are, Mach 1 to 2, as well as hypersonic airplanes. So that's going to be important for that, and it's going to be important here too. We're going to have to deal with sonic boom too, so we're learning from that work.
And a lot of it this is work that you've been doing your entire career here at
Yeah.
Boeing, and to see go from a point where you're working on the initial ideas to getting to a concept and seeing the evolution of this technology, what's that been like for you?
Well, that's been pretty cool. So hypersonics has been around for about 60 years. I've been working for 32, so I worked for half of the hypersonic era. What was neat was when I started work, I started work on the National Aerospace Plane, which was supposed to be a rocket plane, or not, an air-breathing, a single-staged orbit airplane that would fly into orbit. Well, the guys I was working with, they worked on the X-15. So there's a cool continuity there between the guys that worked on the very first hypersonic things and then kind of my next generation working on the next generation with air-breathing, scramjets, and that kind of stuff.
And with that model in your hands, let's once again go back over the particulars of hypersonic air travel when it comes to this passenger carrying concept. Let's walk through the details of what makes this different than, say, current air travel. And again, this is something that could happen, and we're still talking 20, 30 years out.
Right. Yeah, it's a little ways off, but it's neat that we're starting now. We need to start now to prepare for the future. And who better than Boeing, who knows how to build big airplanes, certify complex airplanes than us to be able to do this. So there's really three key features. One is the aerodynamics, how you shape it. A vehicle like this is going to be very slender for low drag. There's a quantity called lift-to-drag ratio, the ratio of the lift you're generating to the drag. That needs to be high. The higher, the farther you're going to go, the less fuel you're going to use. So it's very sleek to reduce drag. On the lift side, we shape it to ride on a shock wave. It's called a wave rider. So we've shaped it to be a wave rider to increase that lift-to-drag ratio. Secondly, what it's made out of, when you fly fast, the skin gets hot. Air friction, it's like rub your hands together fast and they get warm. Well, if your hand's going through the air at Mach 5, it's going to get really hot, over 1,000 degrees Fahrenheit. Here, 1200 degrees Fahrenheit, so we got to make it out of a higher temperature material like advanced titanium. And then the propulsion system. A normal turbo ramjet, turbofan engine isn't going to get you all the way to Mach 5. The air temperature gets too hot. The same reason, the skin gets hot, the stuff inside the engine gets too hot. So you go to about Mach 2 or 3 on that propulsion, then you got to transition to a different mode. In this case, Mach 5, it's ramjet mode. Scramjet is when you're going above Mach 5 and you actually have to burn the air at a supersonic speed. In this particular one, you burn the air at subsonic speed. It's a ramjet, and that's what's in these engine nacelles you see down here. It's an integrated, what's called a turbine-based combined cycle engine. Something combines a turbine engine with another mode like a ramjet.
Another question coming in from our viewers around the world. How long would it take to fly from, let's say, London to New York or New York to London?
About 2.5 hours. 2 hours, 20 minutes, 2.5 hours. Very quick. Quicker than it would take to fly across the United States today.
Yeah, because I can tell you that the flight from Seattle anywhere else is it's a long flight.
I did it last night, Washington, D.C. to here. It was 5 hours.
So you're going on adrenaline and a little coffee this morning.
A little bit, yeah.
So if you're just joining us, we are here talking about our hypersonic passenger carrying aircraft, our initial design concept. The thing that really is crazy to me is the idea of how fast it really goes. That stat you gave of 1 second is 1 second for every mile. So
mile a second.
It truly is incredible.
That's faster than a bullet. It's twice the speed of a bullet. So yeah, in 1 second you're going a mile. That means 3,600 miles per second. And I see a question that came in that's kind of relevant to this topic. Will it require special fuel? The answer is no. Jet A fuel will work fine in a turbine and a ramjet. But you know what? We're also exploring the possibility of liquid methane, because an advantage of methane is it's cold. We're going to have to, the cooling is going to be required here for parts of the airframe, for the air. You have to condition the air for the passengers, so you have to cool it at these speeds. So methane has cooling capacity, and water is another great coolant for things like that. So we're studying those kinds of options and trades.
Within the past couple of years, what sort of advancements in research and development have really helped push this forward?
Several. One is materials. Even though this isn't a real exotic material, titanium, it's still an advanced titanium. So, and propulsion has been a big one. There's been a lot of research and development in scramjet engines, dual mode scramjet engines, ramjet engines, et cetera. And then in the design tools, today we have very fast computers, and we've developed algorithms that we can simulate the airflow around the vehicle. So we actually simulate the flow, we simulate the structure, we simulate the heating. We can simulate those things, and by being able to simulate them, we can now better understand what's going on and better optimize the design. So we can use math actually to what we call explore design space, and let math guide us to the optimum shape, the optimum choice of engines, the optimum choice of fuel. We call that multidisciplinary design optimization. It's a pretty neat thing.
Math is the solution.
Math is, learn, math is good.
Another question coming in from Cliff. He wants to know, will hypersonic speeds be available only over sea, like with sonic booms, or have we even decided that yet?
We haven't, and that's a possibility. It could be possible that if the boom level can't be reduced low enough, that it'd be over ocean only. But it's something that we would like to figure out how to get the boom low enough. And that goes back to the earlier question about NASA. NASA's doing a lot of great work trying to figure out how to shape, how to design the airplane to take that boom down to a low rumble, that it would sound to you maybe like thunder in the distance, and it wouldn't really bother people. So that, so hopefully we can get to that point. It's a little ways off, so we got some time to figure those problems out.
When it comes to driving this type of innovation, what's it like to be on the front end of it, and then also seeing how hard it is and thinking, we can make this happen?
Well, it's a lot of fun. One of my favorite things is to solve really hard problems that they just attract me. So I like doing very challenging things. I kind of like things that are on the edge of too hard, and we figure out solutions to those. So it's just exciting. For me, one of the highlights of my career was that X-51 flying. Back in 1995, I came up with the original concept for what became X-51. So to sit there and watch that actually fly and be the first, really the second time in history that a scramjet was flown, it was the first time in history of that kind of scramjet, was very rewarding, very exciting.
Well, Kevin, another question, we'll probably make this our last question before we switch over to another platform. We'll be answering more questions throughout the morning. James wants to know, how is this different from sonic cruiser technology?
Yeah, it's, quite a bit different. So sonic cruiser meant flying near Mach 1. It was not supersonic, it was still subsonic. That vehicle still had a lot of, optimizing the aerodynamics to do low drag. When you start to get close to Mach 1, there are regions on the vehicle that become supersonic. The air accelerates to supersonic speed. So a lot of, in the shape optimization, the aerodynamics were there. So they're common in that sense that they have to have optimum aerodynamics, but it's very different flying Mach 5, hot, different propulsion system, and flying at Mach 0.92 to 0.94, which is what Sonic Cruiser was looking at.
Well, Kevin's going to stick around for a bit and answer some of your questions that are posted on Facebook as well as Twitter. We want to thank you so much for joining us. And it's going to be really exciting as we see this all move forward, Kevin, isn't it?
It is.
Well, hey, again, thanks so much. Take care, and we'll see you soon.